Humanity was born way ahead of its time. The reason is Grabby Aliens.
Welcome. Today's topic is aliens. In particular, we'll talk about a recent model of how intelligent life expands and distributes in the universe. Its variables can be estimated from observation, and it makes many predictions. For example,
It's got nice animations.
predicts when we should expect to meet another civilization, has things to say about our chances of hearing alien messages, and of becoming an interplanetary civilization ourselves.
Always with the burps.
It also answers why we don't see aliens yet, considering the universe's large number of stars and galaxies. The model we'll discuss is one of the most interesting of its kind, but it's very recent and still not widely known. Its main author is Robin Hanson. You may know him as the person who first introduced the idea of the Great Filter in 1996. He published a paper with 3 co-authors, detailing his new model in March 2021. The model's basic assumption is that some civilizations in the universe at some point become grabby. This means that 1. They expand from their origin planet at a fraction of the speed of light. 2. They make significant and visible changes wherever they go. And 3. They last a long time. But why do we have reason to think that such civilizations should exist? The starting point of the model, the thing that makes it necessary in the first place, is a question. Why are humans so early? To understand where this question comes from, we need to step back and ask another question. What is the probability that simple dead matter becomes a civilization like ours? Robin Hanson uses a simple statistical model introduced in 1983 by the physicist Brandon Carter, and that many others have
A simple statistical model. Doesn't look simple.
pursued since then. It posits that life has to go through a series of difficult phases, from when a planet first becomes habitable to when an advanced civilization is born. These difficult phases are called hard steps. For example, hard steps could be the creation of the first self-replicating molecules, the passage from prokaryotic cells to eukaryotic cells, multicellularity, or the creation of particular combos of body parts. Each step has a certain probability of being completed per unit of time. This model also appears in biology as a standard way of describing the appearance of cancer. One cell has to suffer many mutations before becoming cancerous. Each mutation has a certain probability of occurring per unit of time. The probability of all the mutations occurring in any given cell is low enough that, on average, each cell should become cancerous in a much longer time than the organism's lifetime. But there are enough cells in the human body
That's
that
crazy.
a few outliers suffer enough mutations in a normal lifetime and end up becoming cancerous. The number of mutations required is typically 6 or 7, but sometimes just 2 are enough. Now, let's try to estimate how many hard steps life on Earth had to go through. Hansen notices at least 2 periods during our planet's lifetime that we could see as potential hard steps. First, the period between now and when Earth will first become uninhabitable, which is 1.1 billion years. Second, the period from when Earth first became habitable to when life first appeared, which is 0.4 billion years. If we use 1.1 billion as the typical duration of a hard step, then we should expect Earth to have undergone 3.9 hard steps. If we use 0.4, we should expect it to have undergone 12.5 hard steps. A middle estimate between these two is 6 hard steps. This concept is generalizable from planets to large volumes of space containing many stars.
This is cool. This is really cool. Hard steps.
The number of hard steps appears as a parameter in a function that takes a time t and
I wonder if that's a generalizable rule. You could take that into a smaller micro sense in your own life. How many hard steps in your life have you had to go through? Is there any that you are currently going through? And maybe that's a cool way to view them, you know. Trials and tribulations. 1 step forward, half a step back. Then you're dancing.
returns the probability that advanced life will appear at that time in a certain volume of space. We use this law to estimate human earliness. You don't need to understand every term here, but you should know that n is the number of hard steps estimated, and the L with the bar on top is the maximum lifetime of planets that are considered suitable for advanced life. Varying these two parameters leads to different estimates for how early advanced life on Earth looks compared to past and future advanced life in the rest of the universe, as predicted by the law you just saw. Let's see what each of the two parameters means regarding human earliness. First, a large number of hard steps greatly favors later appearance dates of advanced life, making humans look very early. It makes sense that more hard steps make us look early, because life has to overcome more difficulties. The more hard steps there are, the more unlikely it is that a civilization appears as early as we did. Second, the same is true for increasing the maximum lifetime of habitable planets. This is because Earth is a relatively short-lived planet. It's estimated that it will become uninhabitable in around 1.1 billion years, and the Sun will run out of hydrogen in about 5 billion years, turning into a red giant and potentially swallowing Earth. But
now that's a very hard step.
stars and planets can have way longer lifetimes, in the order of trillions of years, thousands of times more than Earth. The universe itself is just 13.8 billion years old. Therefore, if those higher lifetime planets are habitable by advanced life, then humans on Earth look very early. Why? Because the overwhelming majority of life in the universe will exist on those longer-lived planets in the coming trillions of years. But whether advanced life is possible around longer-lived stars is an open question, because longer-lived stars have lower mass than our Sun. Plus, the estimate for the number of hard steps is subject to variation. But even with this uncertainty, we can look at how early advanced life on Earth is predicted to be by many combinations of values chosen for the two parameters. Robin Hanson does this in this graph. The horizontal axis represents the maximum lifetimes for stars that allow habitable planets, expressed in billions of years. The vertical axis is the number of hard steps. For every combination of those two values, you get a measure of how early advanced life on Earth is, according to the mathematical laws we saw earlier. Colder colours mean that we're not that early. Warmer colours mean that we look very early. You can also look at the numbers. They represent today's 13.8 billion years date percentile rank within the distribution of advanced life arrival dates predicted by the equation we saw. Confused? Here's an example. See that number 1% written on that line? That means that every combination of N and L that falls on that line means that humans are among the first 1% of all advanced life that will appear in the universe.
Whoa. Maybe we are early.
The values that fall to the left of that line imply that we came later than the first 1%, and all the values on the right of that line imply that we came earlier than the first 1%. Let's try a couple more examples. Let's set the maximum planet lifetime at 10 trillion years, and the number of hard steps at 10. We get a rank of less than 10 to the minus 20, which is 1 out of 10 quintillion. We look incredibly, unbelievably early. Now let's try something more conservative. So let's use our middle estimate for the number of hard steps, which is 6, and a very restrictive maximum planet lifetime.
How's the middle number 6?
10 billion years, the lifetime of the Sun. In this case,
Can someone explain that?
we get more or less that we're amongst the first 10% of all advanced life that will ever appear in the universe. So, still surprisingly early. In order to not look early, we have to assume unreasonably restrictive values for the number of hard steps and the maximum lifetimes of habitable planets. So, we're back to the question we asked at the beginning of the video. Why are we early? This is a puzzle in need of explanation. Being early means that we're in an unlikely situation, and when you see evidence that's unlikely according to your models, there's probably a need for an explanation. Something that you didn't expect to happen has happened. Or, said differently, when you encounter a piece of evidence that is unlikely according to your beliefs, that piece of evidence tells you to give more weight to hypotheses that make that piece of evidence more likely. Robin Hanson's solution to this earliness riddle is Grabby Aliens. They serve as the main assumption for his model, and their existence is also a hypothesis that has acquired credence due to the evidence provided by the apparent earliness of life on Earth. Together with this hypothesis, the probability of the whole model built by Hanson gets boosted. As anticipated, the word Grabby means that 1. Such aliens expand from their origin planet at a fraction of the speed of light, 2. They make significant and visible changes wherever they go, and 3. They last a long time. But why do Grabby Aliens explain human earliness? One consequence of Grabby Aliens is that they set a deadline for the appearance of other advanced civilizations. The model predicts that if such aliens exist, they will soon...
Alright, because they take up all the space. Natural life can't evolve on those planets, so a Grabby Alien sets the date for other life. So if you have early Grabby Aliens, all the territory for natural life, spontaneous, unique life around the galaxy, all that territory already has life on it, which, as we know, life usually is a dominating factor on a planet and tends to destroy or take over all the resources so that other life can't proliferate there, evolve and proliferate outwards.
soon occupy most of the observable universe, and when they do, other civilizations can't appear anymore because all of the habitable planets are taken. Therefore, if Grabby aliens exist, ours is not an unlikely situation anymore. Civilizations like ours, advanced but not yet Grabby, can only appear early, because later, every habitable planet is already taken. Before becoming Grabby, every advanced civilization must observe what we are also observing, that they are early. This means that Grabby aliens explain the current evidence. They make it look likely. They make us look not that special anymore. We become exactly what a typical non-Grabby civilization would look like. If you know the history of science, then you realize that looking special is very fishy. To put it another way, before the Grabby aliens hypothesis, we have a situation in which we appear very early among all the possible advanced civilizations in the past and future history of the universe. An unlikely situation. But once we hypothesize Grabby aliens, future advanced civilizations that are not yet Grabby disappear. Their existence is prevented by some of the earlier civilizations, who became Grabby and occupied all the habitable planets on which new civilizations could have been born. And therefore, the Grabby aliens hypothesis makes us look more typical. Every civilization like us will follow the same path of appearing early and then potentially expanding into space. Grabby aliens are also plausible for other reasons. Life on Earth, and humans, look Grabby in many ways. Species, cultures, and organizations tend to expand in new niches and territories when possible. Species expanding in new territories can access new resources and increase their population. Therefore, we should expect behaviors that encourage such colonization to be selected for, and species to evolve to exhibit these behaviors. Imagine two species that consume the same resources. They inhabit two different territories, and they're separated by an uninhabited land rich in resources. One of the two species has no particular impulse to consume more resources. Its population simply remains stable in its territory. The other, instead, expands into the uninhabited territory and makes more offspring. Therefore, this second species will soon outnumber the first. With each successive episode of expansion, the second species will become larger and larger, and evolution will go in the direction of Grabby behavior.
Grabby behavior here, this reminds me of the film Idiocracy, where there's dumb and smart people and a time capsule, and an average man from the present day gets frozen in time, and as evolution goes forward, the argument is that dumb people outbreed smart people by orders of magnitude, and eventually the average intelligence goes down. The average man from the past is unfrozen. He is now the most smart or most intelligent man on the planet, full of the dumb people that were bred. It's quite a good film. That's Idiocracy.
Kind of selection effect looks general enough that it might very well be valid for species on planets other than Earth. In addition, expansion usually means consuming resources and changing the environment. Grabby aliens, if they exist, should make visible changes to the volumes of space they occupy. They might build structures to harness the energy of the stars, such as Dyson spheres or Dyson swarms, build technology on the planets they occupy, and use other planets and asteroids for resources. Even with the tools we have today, some of these changes wouldn't escape astronomy, and therefore can be considered visible to other advanced civilizations. But the idea of Grabby aliens relies on interstellar travel being possible. How likely is that? Even today, we foresee a non-trivial chance that humanity will expand to other planets and star systems. Don't imagine how we would do it with human-crewed spaceships. There are far easier ways. Consider, for example, probes. Self-replicating probes that settle on a planet to plant the seed of a new civilization are plausible technologies in the realm of speculative engineering. They're called von Neumann probes, and they comprise elements that are likely to be developed at some point. Each of these elements already exists in nature or in human technology: a capacity of self-replication, a way to store and possibly collect energy, some kind of AI, manufacturing capability, and an engine. Cosmic distances aren't much of an impediment. There are many possible ways propulsion could be achieved, but consider, for example, solar sails. They're basically mirrors, reflecting light from a star or a laser, and accelerating due to the force exerted on them by the light. With solar sails, it's possible to reach significant fractions of the speed of light. Even at lower speeds, estimates for colonizing the Milky Way range from 5 million to a few hundred million years. Very little when compared to the age of the universe, or even the age of the Earth. But we'll see that the Grabby Aliens model invokes speeds at least as high as 1/3 of the speed of light to explain why we don't see any trace of aliens in our skies. Perhaps there is just a tiny chance for any Grabby civilization to arise, but even in this case, they'll have a disproportionate impact on the universe. If Grabby aliens exist, they'll spread through the universe relatively soon. In the next video, we'll talk about how soon and when we'll meet them.
Relatively soon means thousands, millions of years, a billion years.
along with many other predictions. If you want to know more, stay tuned.
Hey, Scriptwriter here. This has been our most difficult video so far, but we want to make more content like this. If you want to support our work and see more of it, pay a visit to our Patreon page. You can find the link in the description. Speaking of Patreon,
Interesting video. Grabby Aliens. Life that tends to destroy the capacity or attributes, characteristics of planets and environment that would allow individual and new and unique life to rise across the galaxy. Early Grabby Aliens. We might be one of those species, Elon. We are one of those species, Elon.